All right, let's talk about trees. So, your idea of what a tree might be from nature is very similar to what a tree is in graph theory. So a tree is a graph that is connected and has no circuits. All trees have the following properties. There's only one path joining any two vertices. So if I wanted to get from F to A, I have to go through E, D, C, B, A. If I wanted to get from H to D, I have to go H, G, C, D. So that's going to be true for any tree. Every edge is a bridge. So if I remove an edge, it will basically make it disconnected. A tree with n vertices has n minus 1 edges. So this guy has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which means it should have 9 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. I've got some more examples of what is meant by a tree and not a tree. And what I've done is I've put a tree next to something that's not a tree, and we're going to explain why these are not trees. So my first example looks kind of like a spider. It still holds true. It's connected. Every edge is a bridge. It holds this property. Down here, this is basically just a line with vertices connect along the way. But if we look at the next one over here, this is not a tree because it has a circuit. So this makes a circuit. That is not allowed. And so why is this one not a tree? So not a tree. This is not a tree because it is disconnected. Okay, that vertex D living out in space, part of the graph, so this is now 2 pieces, so it's disconnected. All right, so these are not trees because of those reasons. All right, so let's look at this example. So what we're going to do is we're going to be finding a spanning tree of this. Let's talk about what a spanning tree is. Basically, it is a subgraph of a graph. So this is our given graph. This is not a tree because it has circuits. Okay, this is not a tree. But what we want to do is make a spanning tree, which means that we are going to remove some of the edges of the graph so that it is a tree. But we have to maintain the same vertices. Okay, so we have the same vertices. It's connected, but it has no circuits, and it only includes edges that existed in the original graph. So let me give you some solutions, and I think I want to give you not solutions as well. So the following are solutions to this question. The basic shape is good enough. Really oops, that's not a solution. I have a circuit. I'm going to put my vertices in the same area, but it may be slightly different because it's hard to draw the same lengths and things. All right, let's try again. So this is now going to be a solution. Let me use my marker here. I like to always emphasize my vertices. All right, so we put A, B, C, D, E, F. All right, so this guy is a spanning tree. I can give you another one. There's several that we could come up with. That's an example. I guess this is also a solution. Instead of removing AB, let me just keep AB, and I'll go down here to C. Clean this up. So here's B, A, C, D, E, F. This is a tree. B, A was in the original, C was in the original, F, E, D. Okay, make sure. All right, so that is a solution. That is a solution. You could probably come up with another solution. This is not a solution. In the homework, I think some of these are multiple choice, and I want you to see why something is not a solution. Let me first place my vertices approximately where they go. Okay. Let's do A, B, D, E, F, and I'll do this one, C. So this is a tree, but why is it not a solution? So think on that. Why is this not a solution? So this one is not a solution because BD was not an edge in the original or given graph. Okay? So just because the answer is a tree, if it doesn't have the original edges, if they have extra edges, it's still not a spanning tree. Now, before we go on to the next idea, we have to understand what is meant by weighted graphs. If you watch some of the other videos, you've probably seen what some examples of some weighted graphs are, but let's just revisit it. We have time. So, a graph whose edges have numbers attached to them is a weighted graph. Just so you understand, there's an example. The numbers shown along the edges of a weighted graph are called the weights. So these red numbers are the weights. And there are also quantitative ideas such as cost, miles, distance, etc. And generally we want to minimize those things. So a minimum spanning tree, basically it's a spanning tree that we just discussed, but it's going to be the spanning tree that has like the smallest total weight. Okay? So a graph can have many spanning trees, as we previously saw. If we found all the spanning trees and compared the weights, it would take too long. Because if we have this many vertices, there's lots and lots of possible spanning trees. So, in order to find the minimum spanning tree, we'll use Kruskal's algorithm. Pretty straightforward. If you understood Traveling Salesperson, I think this is similar, kinda. But what we're going to do is we're going to take this example, use those steps, and then we'll work this one out. All right, so find the edge so for the Kruskal's algorithm, we're going to find the smallest weight in the graph. Now, before I work it, I'm going to go through these steps because I'm going to work it using the steps, but kind of approach it or display it a different way. All right, so what is the smallest one? Let's go ahead and find it and highlight it. This is a mistake vertex. It's not real. Looks like 8 is the smallest. I think 8 is the smallest. So I'm going to highlight it lightly, and I'll come back and highlight it darker. So we're going to do that again, and we're going to keep doing that as long as we do not make any circuits. That's the big thing. If a number shows up multiple times, 12 shows up multiple times, you choose either one, it doesn't matter. But the way I recommend working these, kind of keeping up with all of these numbers, is I suggest write out or write down, I say vertically, but you can do horizontally if you want. Write down vertically all the edges or edge weights, smallest to largest. And just a suggestion, leave a little bit of space between each of these. Because if I skip something and I need to put it in this vertical column, if I leave a little space, I can squeeze it in. I'll show you what I'm talking about. So I think the next one is 12. We've got two 12, so I'm going to leave a little space. 12 and 12 is the same, so I don't need much space there. All right, I know there's a 14 there, but I'm going to say I didn't see it. So now I'm going to move on to the next one, which is 21. Notice I'm also circling these as I write them down. That way, at the end, I'll know if I've got them all. All right, then I continue, 21, then I got 25, and I realize, oh, there's a 14. I should put that right there. Okay, so if I had room, I could do that. All right, 20, I got all the 20s, I got all the 20s, 33, 35, and I got two of those. Looks like 42, 45, and then 57. Okay. Always like to count all my circles, make sure I've got everything circled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we wrote down vertically all the weights, largest to smallest, and circled them as I went along. The next thing I'm going to do is start highlighting. So I guess that's my first step. My second thing, I'm going to highlight edges, I guess smallest to largest, until I get circuits. If you get a circuit, if an edge makes a circuit, skip it, go to the next. Okay, so we get the first one for free. I like to highlight them as I go along. Okay. The next one is 12. Does this 12 make a circuit? No. It's not even connected, but that's okay. It will be eventually. Does this 12 make a circuit? No. So I'm keeping it. If I highlight it, I'm keeping it. Does this 14? No. 21? No. 25? Almost. No. 33, 33 does. If I highlight this, I get a circuit. I'm going to cross it out. But I might not be done. I might be done, but I might not be done. Some examples, once you hit this first one, they stop, but then some of them, one of these will be correct. 35 makes a circuit. 35 here makes a circuit. 42 makes a circuit. 45 makes a circuit. And 57 makes a circuit. So the only ones that work are those. So I think many of the homework questions, many of the multiple choice, these are multiple choice, and you kind of pick out the shape that looks like this. Now, they want the minimum spanning tree done and give the total weight. The total weight, I guess this is part 3, total weight is found, total weight is found by adding these. And when I say these, I mean the highlighted ones. All right, so let's do that calculation. All right, looks like I'm going to do it a couple of times. 8 plus 12 plus 12 plus 36. 8 plus 12 plus 12 plus 24. Let's just do it here. 8 plus 12 plus 12 plus 14 plus 21 plus 25. I got 92. I'm going to do that again. 8 plus 12 plus 12, 14, 21, 25, 92. Okay, so there you go. Some of these will be a little more complicated than this. Some of them will be even easier. But that's the idea of Kruskal's algorithm.